Okay, hello everyone. Dr. Phil here again. I am redoing this because apparently last time I did it, you guys couldn't see my screen. So hopefully this will work and it'll record. So I got to about slide 65 last time and didn't record. So I'm going to just do as much as I can right now. I have a Zoom meeting at 7:10 with a student, so I'll see what I can do here in the interim. So I'll go over this again. So matter is anything that takes up space and has mass. And as I mentioned before in the other video, um, we all have matter, but without getting into quantum physics, please realize that everything we're touching right now is literally empty space and it's all energy and it's compacted into physical form for this physical reality we're in, but we won't get into quantum physics. But as far as for biochem or whatever, we'll go that far. So atom is the smallest chemical units of matter. We won't get into subatomic particles or quarks or things like that. So, so I'll go into the electronic structure. Electrons are negatively charged subatomic particles circling a nucleus. So we're going to be seeing later, we're going to see diagrams of a nucleus that contains your protons or the positive charge or neutrons with no charge, and then orbiting around them, the octet rule are going to be these electrons, all right? So in a perfect world, the amount of protons in the middle with a positive charge are going to equal the amount of electrons on the outer surface in a perfect world. And then we're going to talk about a valence electron. So protons, neutrons, electrons, croutons, whatever you want to remember here. This should also be on the worksheets I sent out. Not sent out, but I put in your course for chapter 2. The nucleus is a structure that contains the neutrons and protons. And kind of remember, neutrons have no charge, protons have a positive charge. When we start talking about having more neutrons than protons, we could get into like radioactive half-life, and as these neutrons are ejected, they're giving off energy, and we could harness that energy and heat things like with a subatomic nuclear power plant. We could captivate that energy and convert it just like our atmosphere converts the energy from the sun. You know, we all learned it's very, very hot. But right around the sun, it's minus 400 degrees centigrade. So it's like below absolute zero. And then that light energy comes through the universe and hits our planet, and our planet is able to literally convert that light energy into heat that we feel as heat, and then we can convert that to solar energy, and the plants can convert it to energy using chlorophyll, and then we consume the carbohydrates and we can convert that into ATP to power our cells through the Krebs cycle, you know, without getting into all of that at the moment. We'll talk about that throughout the course, right? So neutrons are uncharged particles, zero. Protons have a positively charged particles, and then we'll, like, once again, we'll talk about neutrons and protons, and isotopes will have a different number of neutrons, or they should have the same as protons, but if they have more or less, we can carbon date something and figure out how old it is, because as the nucleus is ejecting these neutrons, we can figure out a time span of when they would, how they would eject them, and then we can I don't want to say carbon date it, we can date how long the structure was around for. All right, so here are your protons, positive charge, and neutrons are here, zero, it says right here, and the electrons are going to circle around here, all right? So if the math is correct, we have 1, 2, 3, 4, 5, 6, following the octet rule, go 2, 8, 8, but we have 6 there, so we should theoretically have 6 protons and six neutrons in there, right? And we do. And as far as atomic mass and things, really your protons and neutrons actually have weight. The electrons have weight, but it's relatively negligible. So if we're looking at atomic mass or atomic weight, it should be the the weight of the neutrons and protons, and it should be a definitive number. So like this should literally be 12. But if it was 12.6 or something, we're going to say, well, that's because there may be an extra neutron in that area, but we'll talk about that maybe later or maybe not at all. So atomic structure, we have elements composed of a single type of atom, and these are on the periodic table. And I uploaded a short video on the periodic table and how you can kind of read those vertical columns. They're all going to have the same number of valence electrons in their outer shell. So they should all react relatively similar. All right, and then we have periods going horizontally one way, and then the columns we're going to talk about, or we'll talk about how they have valence electrons and how we want to combine them to fill in the outer orbitals of these valence electrons. So whether it's going to be ionic bonds, covalent bonds, nonpolar ionic bonds, or so on, we'll discuss that. So once again, the atomic number is equal to the number of protons in the nucleus, number of positive charges. The atomic mass, or atomic weight, depending on what you're talking about, is the sum of the masses of the protons, neutrons, and electrons. And like I mentioned, electrons have, we're going to say mass, but it's negligible in comparison to the larger number of protons and neutrons per se. So there's a bunch of table of common elements of life. So we're going to be only dealing with a lot of these in chemistry, biochem, microbiology, or whatever you're going to be taking in the science field. So hydrogen, atomic number 1, that just tells me it literally only has, if it only has one something in the nucleus, it has this equal amount in the valence electrons. So hydrogens are very tiny. There's a very weakly electronegativity. So hydrogen bonds have a positive charge. They like to give up that electron to other elements to form compounds, and they're relatively easy to break. All right, and then boron, carbon, we'll see is going to have 4 bonding sites, because we know by the octet rule there should be 2, and then 8. So there's 2 in the first shell, 4 around it, and 8 minus 4 is 4. So we know it's going to have 4 bonding sites. And if we threw a hydrogen on each one of those, we'd have methane. And methane was some of the first carbon sources for a lot of the archaea that were here millions and millions of years ago. So remember, if we try to figure out how long we've been on the planet, if you had a clock in front of you going from midnight all the way around twice, 24 hours a day, we literally appeared at 11:59 p.m. compared to everything else that's on the planet. So you can wrap your head around how we've been around for tens of thousands of years, depending on what you believe in or what you're reading. What we just showed up recently on this planet. All right, and we'll go over some of these if we need to. Chlorine, we'll see this has 7 valence electrons. It's relatively full. It wants to grab an electron from somewhere. Potassium is always a positive charge. It likes to give that up, or it likes to connect with things. And we'll see that. So isotopes, if I ask you a question on an exam about an isotope, these are very similar elements, but they're going to differ in the number of neutrons in the nucleus. Protons, positive charge, neutrons have no charge. This is where the majority of the atomic weight comes from. So we have stable isotopes and unstable isotopes. So unstable isotopes are going to start ejecting. Once again, they start ejecting productive half-life. They start ejecting these. Sorry, guys, I just spent like 3 hours at Millard. My throat is, I don't know what I breathed in over there. Wasn't good. They're going to start ejecting these neutrons. All right, and we can, like I said, we can release energy during their radioactive decay. And if we want to, we could harness that energy. And we do, or we used to, ever since, Chernobyl and stuff, that we're a little more cautious. West Valley, if you're familiar with the area, south of here, sort of near Springville. I don't think that is active anymore. I think they do have staff though, making sure that nothing leaches out. We don't want that stuff leaching out. Or, you know, if you're looking at Hooker Chemical used to dump a lot of stuff in the water, and we won't even talk about the wetlands where, you know, you have a frog with 3 eyes and all kinds of weird stuff. I'm digressing. So if we want to carbon date something, all right, you know, we were talking about carbon dating it. So we could say carbon 12 should have 6 protons and 6 neutrons. That's completely normal, right? So protons should match neutrons. When they don't, we have extra neutrons, right? And as these things start ejecting these neutrons, because there's no charge to them, they give off energy. And whenever we break bonds, we give off energy. And we'll talk about that with dehydration synthesis or hydrolysis, dehydration synthesis. We'll talk about combining things takes energy. And when we break it apart, we release exothermic or endothermic reactions. So electron configurations, only electrons of atoms interact. So they determine atoms' chemical behavior. When we see a periodic table up here, I'm going to just, if I remember what I did this morning when I did the video, I'll just kind of show you how things, or things that you've heard of, would react and why. Right? So electrons occupy electron shells, and remember, there's the octet rule. And then valence electrons are going around the outer surface. Electrons in the outermost shell that enter atoms. And remember, the only one that's going to interact is the outer shell. The inner shells are stable, and they're literally near the nucleus where the protons and neutrons are. And think of that as a great big magnetic force. They're there, they're held tight in place. The valence electrons are further away. They have a little bit more freedom. The grip of the nucleus isn't there as tightly. So whenever something's going to react in normal circumstances, I'm not going to get into nuclear fusion or anything like that, or quantum physics, but it's going to react with the outer shell in a pretty definitive pattern, or a pretty definitive pattern. All right. We're not going to get into 3sp and hybrid orbitals. That's a little bit behind the course, and it made my head hurt just even remembering that. All right. So here's our first shell. All right. And then our second shell, these are going to be different orbitals. These are your sp orbitals. But we're going to be really dealing with, this is a 3-dimensional view. These are sp orbitals and how they would likely be. All right. So if we're talking about quantum physics, this thing is in, number one, it's in 2 different places at the same time, and just observing it is going to change its behavior. We won't even get into that. But here's our first shell and our second shell, and we have our valence or octet rule. So it's always going to be 2 and then 8. This is the first shell. This one's around it. So here is 2 and then 8 and then 8 for the octet rule. All right, so here's a periodic table. This is just some of the things that you've probably heard of, or some things that are common. All right, hydrogen really doesn't even honestly belong there. It should be a separate. You'll see it over here sometimes on different periodic tables because it literally is a gas. All right, all right. But everything in here, if you look, all right, and you can make this boring and tedious, or you can say, oh, this is pretty cool. If I actually learned all this, I could figure out how things would react, or I could substitute one for the other and they would bond totally. So this has 1 valence electron in its outer shell. This one has 1, this one has 1. This one, this is, if we number these, are 1, 2, 3, 4, 5, 6, 7, and so on. All right. But if we look at these, they're all going to have 2 valence electrons in the outer shell. All right, this one's going to have 3. All right. And remember, this outer shell wants to have, well, this one wants to have 2. This one here wants to have 8. So rather than finding 7, it's going to find something that has 7 and bind with it. So if you want to think of table salt, sodium chloride. So this one has 7 right? So it could theoretically, it could bind with anything with one electron, right? So if I bound it with HCl, that's hydrochloric acid, all right? Not cool. Um, sodium chloride or potassium chloride, right? So these things are going to bond depending on oxygen, 2, 4, 6. We need 2 more electrons. So I could combine oxygen with 2 hydrogen, H2O, water. Or we could bind it. We could theoretically bind this with 2 lithium. The combinations are kind of cool. You could just combine anything you want as long as the math adds up and they're in the same column. They're going to have very similar characteristics, right? So it says here, the publisher put the slide here. Electrons zip around the nucleus about 5 million miles per hour. Why don't they fly off? Well, because they have that electronegativity, the gravitational pull, you can think of it, of the nucleus that contains the neutrons and protons, holding it in its atmosphere, okay? And, we could picture them as rings, but literally they're orbitals, all right? And they could be potentially anywhere in that molecular pattern. So valence, remember, combining capacity of the atom, valence is the outer shell. It's positive the atom has electrons to give up, negative if the atom has spaces to fill. Stable when outer electron shells contain 8 electrons. That's the octet rule. So it's going to do whatever it wants. So if it has 1 electron, it wants to give it up. All right, it's releasing an electron. So if you want to remember oil rig, OIL, RIG. So oxidation, it loses it. Reduction, it gains it. Remember, an electron is a negative charge. So if it gives up a negative charge of electron and something else grabs it, the other item is reduced because it literally took on an additional negative charge. It's actually reduced. That should kind of make sense to you. Or if something loses an electron, so if we're saying it gains it, it's reduced. All right. If it's oxidized, it loses it. If it is reduced, it gains it. Gains an electron, it's reduced. If it gives up an electron, it gives up a negative charge. All right. All right. It's oxidized. All right. And if you don't know what oxidation is, just look at any car out there or any piece of metal that's been around for a while. Rust is oxidation. So it's stable when the outer electron shells contain 8 electrons. It will do whatever it can in the majority of cases to fill that outer shell. It wants to be stable. All right. Chemical bonds, atoms combine by sharing or transferring valence electrons. And we'll talk here about covalent. So valence is the outer shell, covalent. So we're thinking covalent. Well, generally things are going to share. They're co-sharing these things. And so both of them, when they share them, they kind of lock together, but each element has their outer valence electron electron shell filled. So a molecule is 2 or more atoms held together by chemical bonds. And a compound is a molecule composed of more than one element. All right, so a lot of times you'll get molecule and compound mixed up. All right, so a molecule, you can have a molecule of water, I could have a molecule of something. 2 or more atoms held together by chemical bonds. All right, so I could have a molecule of oxygen or a molecule of hydrogen, as long as they're held together by chemical bonds, 2 or more atoms held together. So if hydrogen each has 1 valence electron, if we bond the 2 of them together, H2, all right, the outer valence electron, which happens to be the first electron shell, would have 2. All right, a compound, a molecule composed of more than one element. So if I had oxygen, it has 6 outer valence electrons. If I add 2 1 valence electron hydrogens, I have H2O. That's a compound. All right. You'd say, well, I have a molecule of water. Well, technically you do. 2 or more atoms held together by chemical bonds, but it's also a compound because it's made out of more than one element. All right. Or if we're talking about methane would be a compound. It is carbon with 4 empty valence electrons. We add hydrogen to each one of those. It's full. All right, that's a compound. A covalent bond, sharing a pair of electrons by 2 atoms. All right, they're literally sharing it. Codependent, covalent. Sorry. Electronegativity. Attractions of atoms for electrons. And the bigger the, some of these elements are very electronegative, like oxygen is very electronegative. And when it binds with 2 very tiny hydrogens, it has very, very specific electronegativity properties. Instead of, oxygen and 2 hydrogens, you would think, well, oxygen would be in the middle, 2 hydrogens would be on each end, that would be at the 180. It's not, it's really at the 105, that angle. So the oxygen or the hydrogen, one becomes very slightly electronegative, and the other ones become slightly positive. So they're not exactly neutralizing each other out, and that gives water some very specific properties. All right, and as I mentioned in the other video, we think of water as having a solid state of ice, liquid state of water, or a gas state of steam, but there literally is a 4th condition of water they recently found. We won't get into that because that's not the the biology dogma they like to teach you right now. All right, and like I mentioned before in the other video, water has very, very distinct properties at 4 degrees. It also has a slightly different bonding structure at 4 degrees. Beyond the scope of the course, but interesting if you like that thing. So the more electronegative an atom, the greater the pull its nucleus exerts on the electron. So if it's really, really electronegative, just think of that as either very, very dense, or it has a lot of pull on those valence electrons. It holds them really tight in space. It doesn't like to let anything go. It holds it really, really tight, like a helicopter mom. Good Lord, I'm dying here. What time is it? Okay. So this is a periodic table. All right. So these are different columns: 1, 2, 3, 4, 5, 6, 7, 8. So thanks, Dr. Phil. I can totally add. Great. But we know the outer shell, oh, these are the noble gases. All right. So their outer valence electrons are completely full. So if we kind of think about that, so their valence electrons are completely full, everything's stable. These are inert or noble gases. They don't want to be bothered with anyone. These are noble gases. They can't be bothered with anyone. Their valence electrons are full. They're at 8. The octet rule says 8. This is 7. So fluorine, chloride, chlorine, bromine. These are halogens. All right. So they have 1 valence electron. There's 7 in their outer shell. They need 1. So we could literally, like I said before, we could take anything that has 1 valence electron in their outer shell. The inner shells are full, except for helium. That, like I said, that's hydrogen. That doesn't even belong here. So I could take sodium chloride, and we could draw that out. I could draw a chloride and do all the good Lord, it's not going to work. I should change the pen color. So I could do chlorine here. All right. I could do its first shell. This is terrible. 2. All right, the next shell should have 8. 1, 2. I'm going to scrap this pretty soon because this is really bad. Oh, it's like an acid sketch. It's terrible. All right. Depending on the atomic weight. So anyway, we get down to this, and let's just say it has 7 here, And this sodium, say this first shell has 2, or whatever it happens to be. All right, and the outer shell has 1 electron. This is going to come over here. They're going to join together. So this outer shell of both of these have 8. And when I get to school tomorrow, on my desk I have a pad I can draw on. So maybe I could do something better than that disaster I just drew there. So anyway, non-polar. All right, so when you think of polar, I want you to start thinking of, well, the poles, positive and negative. But if something is polar, it generally means that either positive or negative, or one side of it has a little bit more polar energy or a little bit more something. It's polarized in one way, either positive or negative. So it's going to be slightly skewed one way or the other. So shared electrons spend equal amounts of time around each nucleus. These are nonpolar. So atoms with similar electroactivities, no poles exist. So that's nonpolar. But if something is polar, we'll see coming up, it's going to spend more time on one area than the other. All right. And oxygen and hydrogen, so water, is sort of, it has polarity and it has very weird electronegativity to it. And polar water is going to be it's a very unique structure. It's a universal solvent. It has different states. And literally, if you want to get into quantum physics and things like that, it actually holds energy, it holds information. If I mentioned before in the other video, if you really want to learn something or find something really interesting, learn about the movie called The Secrets of Water. So literally, water can hold information, it can hold emotion, it can hold a lot of different things. And if you want something else, if you want to see the holographic universe, they can tell you that there's studies where holographically your blood can hold images. Oh, I should probably stop. I should probably have me locked up. The holographic universe is a fascinating book and movie if you ever want to see that. If you're up one night and you want to learn something super cool about quantum physics, definitely a good watch. So carbon atoms form 4 nonpolar covalent bonds with other atoms. So we saw before on that periodic table that carbon, due to its atomic structure, carbon has 4 valence electrons on the outer surface that are on this outer valence electron shell that are unfilled. So it wants to find 4 of something. So it can double bond to something, or we could just simply put for something from the first column with a positive charge, attach it to that carbon, and then we can form a structure. Or if we're talking about carbohydrates or lipids, carbohydrates are going to have a molecular formula of 1-to-1, carbon, hydrogen, oxygen. And talking about if it's fully saturated or partially saturated, or tris or san, cis or tran, we can double bond it, or we can go in and we can manipulate it. We can break those double bonds, and we can make some trans fats and things like that. But this is a nutrition course, so we won't even get into that. So carbon atoms, like I said, they form 4 nonpolar covalent bonds with other atoms. Organic compounds contain carbon and hydrogen atoms. So if you want to take organic chemistry, it's literally going to be anything that has carbon or hydrogen in it is going to be your organic chem. Inorganic chem doesn't contain carbon. All right. And then you learn about chirocarbons or mirror images or dextrorotatory or levorotatory. Yeah, carbons. All right. My head's pounding just thinking about that course. All right. So hydrogen, I said before, is this a molecule or an atom? So it's 2 different elements, they come together. Now their valence electron is complete, all right? So that is relatively stable right there. Right. It's a hydrogen atom, right? Here's oxygen. Now both of these oxygens have only 6 valence electrons in their outer shell. They're both missing 2. But if we join these 2 together, they're going to share 2. All right, so now I have a oxygen double bonded. You can see the 2 bonds there, right? Now the molecule of oxygen. Did I say that wrong? Is it an element? Oh, 2. Good Lord. All right, so there's hydrogen and carbon. We're going to add that on, and now we just created methane. Right? The simplest thing you can make with carbon. 1 carbon, throw 4 hydrogen, you've got methane gas. Now you've got the original carbon source for all the prokaryotic bacteria and archaea that originally inhabited the planet. They were methane consumers. That's where they got their carbon source from. And then the eukaryotic cells came along, and we had a prokaryotic engulfing another prokaryotic, and then we turned into a eukaryotic, and then we actually turned that original prokaryotic bacteria into our mitochondria. And when we start talking later on in the course, you're going to realize that bacterial ribosome and your mitochondrial ribosome and you as a human, extremely similar, right? The rest of your ribosomes and the rest of your body are eukaryotic, different, right? Beyond the scope at this point, this juncture. And there's other things we could make formaldehyde out of this. We have carbon. It's going to have 4 empty valence electrons. Well, hell, we just put 1 there. So it has 4. So we need 3 more, right? So if we add carbon to hydrogen, we did. All right. So that's 2. And we need 2 more. Well, we're just going to take it from the outer shell of oxygen because it had 6. Now we're going to share these 2. All right, now we've got a covalent bond there. All right, and these things are pretty electronegatively similar right there. So polar covalent bonds, remember I said polar is going to be slightly, one element's going to have a little bit more pull than the other generally. All right, so unequal sharing of electrons due to significantly different electronegativities. Most important polar covalent bonds involve hydrogen because hydrogen only had that 1 valence electron. So they're pretty weak, all right? Allow for hydrogen bonding. Hydrogen bonding happens very, very quickly, but it unhappens very, very quickly too. And water, I'm hoping that you've all at least heard this before in high school biology or Survey of Anatomy, Physiology, Human Bio, or something, one of your other courses. I mean, that should be a very, very key component. And once again, we're going to grab these hydrogens, they're going to share that, sort of. All right, but I said before, if these were equal, these would bond at the 180. They don't. Instead of an angle of 180, they have an angle of 105. Very, very specific. And I said these are going to have slight electronegativity. Oxygen's going to be slightly negative. Hydrogen's going to be slightly positive. It's almost negligible, but it is there. It gives water some very specific properties. All right, ionic bonds. So remember, ions are going to be either positive or negative charge. And this is what runs currents. These are what run your sodium potassium pumps. All of these things, all these processes in your body, they literally are run on electricity, if you want to think about that. We kind of think, well, it's chemical in nature. It's also electro, it runs on charges, so it's electric in nature also. So we're talking about charges on the sarcolemma. If we're talking about switching the charge inside the cell, usually should be slightly negative always. Or if we're switching that, we actually turn the cell on or off, or we turn the cell on or off, or cause it to charge or discharge, or produce something or not produce something. We all do it with electrical charges. There's similar to light switches, if you want to think about that. Occur when two atoms with vastly different electronegativities come together, we have an ionic bond. All right, so we're always going to have a positive and negative. They come together, and these are always going to form a salt. So you're going to think of salt as just sodium chloride, could be potassium chloride, but anything that is positive and negative that comes together generally is a salt. All right, we're not going to get into the metals and the colloids and things on the periodic table in this course, but you might want to at least watch that video and refresh your memory if you didn't learn it. Because like I said, it could show up on your NCLEX or another exam. So you might as well kind of learn it. Atoms have either positive cation or negative anion charges. Right. Cations and ions attract each other and form ionic bonds. So these are positive and negative. These are ions, and they form ionic bonds. That should be, relatively simple. Positive and negative come together. They're ions that forms an ionic bond, and typically form crystalline ionic compounds known as salts. So if you wanted to heat some water up, I mentioned this before in the other video without the slide show, get a beaker or something, boil some water, throw, if you want, throw a half a container of salt in there, dissolve it, because as you heat it up, you learn from earth science in 9th grade or whatever that it would, the solubility increases with the amount of heat, the amount of energy put in the system. All right, so you could dissolve all that salt and then let it cool and let it evaporate. All right, and that will form a crystalline structure. So when you're dissolving that through diffusion, that salt should be equally distributed in that very equidistant in that water. But as it cools and as it evaporates, it's going to start forming a crystalline structure. All right. So the interaction of sodium and chloride, I drew this sort of before badly, so thank God it's here. So here's chlorine atom. All right, it has only 7 in its outer valence shell. This one has 1. They're going to come together. Sodium always has a positive charge because it's got that 1 free electron. It's always going to give it up. Remember, if it gives up a negative electron, it's going to have a positive charge. This is going to take on that negative charge. Is going to become more negative. All right, so these are ionic. Positive, this is negative. They come together. They form sodium chloride. And we could use potassium or lithium. Anything in the first column would work, right, due to the chemical structure and the chemical nature. We can predict it's going to happen by the chemical nature of it. There's association of sodium chloride and water. So literally this is, if you look at salt under a microscope or a magnifying lens or a dissecting scope, you're going to see a very, very structured unit. All right, sugar is kind of similar. It's a little bit different shape. But if you dissolve it, it breaks it all apart. You throw it in water, it literally dehydration synthesis or hydrolysis. So if I put this in water, we perform hydrolysis. It literally cleaves, those bonds, all right, and separates sodium into chloride. It's floating all around. Now, as the water cools and evaporates, we have dehydration synthesis. So we take the water out, it synthesizes. Sodium and chloride come back together, and they're going to come together in a crystallized form. All right, so hydrogen bonds are electrical attraction between partially charged hydrogen. All right, remember, there's always a positive because they have that 1 electron always floating around. It's not going to really, it doesn't like to be like that. It wants to give it up to something else. All right, it wants the outer shell to be full, so it's going to want to give it up so they can share that when they bond. Each one of their outer shells, hydrogen and whatever halogen it connects to, will have their valence electrons full. All right, and full or partially negative charge on the same or different molecule. So we could theoretically, we could get two hydrogens to come together. They'll do it, H2. Weaker than covalent bonds, but essential for life. Helps to stabilize 3D shapes of larger molecules. So hydrogen bonds, literally, they help stabilize the 3D structure of a tertiary protein or things. But remember I said, hydrogen bonds, they tend to give up their electrons easily. So they form easy and they unform relatively easy. Right. So there's some hydrogen bonds, just kind of showing you some structure, some nucleotides there. All right, so nonpolar covalent bonds, they're sharing pair of electrons in nearly equal shared between two atoms. So they're nonpolar. Remember, polar is going to be, one's going to be more electronegative than the other. So they kind of unequally share. So it's polarized or different. Nonpolar, remember, nonpolar, they're going to share. They're relatively similar chemical nature of whatever the two things are. Polar covalent bonds, one's going to pull more than the other. So that electron is going to theoretically spend more time in the orbit of the stronger element, the one that has, it's more highly electronegative, or just think of something that has more protons and neutrons. It has more weight or mass, and the more mass you have, theoretically more, think of it as gravitational pull or whatever towards that. Ionic bonds, remember, these are going to be a negative and positive come together. Electrons are stripped from a cation by an anion. Cation is always going to have a positive charge. Anion is going to be negative charge. So electrons, we pull the electrons from the positive charge. And remember, if you lose an electron, it's oxidized, all right? And if it's reduced, all right, it gains electron, it pulls it away, all right? So hydrogen bond, partial positive charges on hydrogen atoms are attracted to full or partial negative charges on other molecules or other regions of the same molecule. So the hydrogen bond, remember, it's very, very tiny. It has that small, weak little positive charge. So partial positive charges on the hydrogen atoms, they're partially positive, that little free-floating electron. It's going to want to give it away. So it's got that little slightly tiny, tiny positive charge. It's attracted to full or partially negative charges. It's going to find anything that's negative, like a magnet, to come together to, all right, and form a bond. Okay. For that. All right, so got a few minutes here before I completely lose my voice. All right, the making and breaking of chemical bonds. So involve reactants and products. So biochemistry involves chemical reactions of living things. We're going to do a little bit of biochem in here. And I just mean scratching the surface. So if you hear these things or see them come up, or if they're on your MCATs or OCATs or whatever, you'll have an idea of what they're asking you. All right, so a lot of students have a problem, not that they don't know the information. A lot of times they don't know how to read the question. They don't even actually know what they're asking or how you would eliminate one of the choices. So in here, it's going to be multiple choice. If you're going into nursing or some of these other things, it's going to be multiple multiples, or it could be all that apply, or what's the order. So, nursing boards and med boards are even harder. But at least for here, we want you to get it, start learning the process of how to take a test. So what are they asking you? What is your answer? What's your distractor answer? What is the throwaway answer? It's usually going to have 4 or 5. So usually it's always going to be a definitive answer. There's going to be distractor. Oh, it sounds right. There might be something a little bit different about it, or something slightly wrong about that. So you want to make sure you know the real answer from the distractor answer, and then you know the throwaway once it's just related to the subject or related to the content, but it's not actually the answer. That's an aside. So synthesis reaction. So when we synthesize something, we put it together. So remember, there's dehydration synthesis or hydrolysis. So lyse means to cut or cleave. And so hydrolysis, hydro always is going to mean water, unless you're in Canada. And then hydro is your electric, and because it used to be produced by Niagara Falls. But the turbines used to call it hydro. But hydrolysis, so if we throw water at it, it's going to cleave it apart. If we pull water away, we pull a hydrogen and an OH off of something, we pull it off, then whatever we're pulling it off of, they lock in together, they chemically bond. All right, so hydrolysis, the example I always give students is if you are going to do dishes by hand and you want to soak them overnight, why do you soak them? And people say, well, they clean up easier. Because you're throwing water at it, hydrolysis, you're cleaving all these bonds. You start breaking away the food particles, or if you burn something on, you start breaking it up. You're going to use the power of hydrolysis to break that apart. So it involves the formation of larger, more complex molecules. All right, so synthesis reactions are literally what happens in your liver when you're putting things together. So if you're eating something chemically to break down your stomach and you digest it with your enzymes or whatever, it's in your digestive tract, in your microbiome, you're breaking it down until it's absorbed into your intestinal capillaries or your lymphatic system and the digestive tract, and we send it through the hepatic portal vein into your liver. Liver's going to take those peptides or small nucleotides, they're going to reform them. They're going to perform a synthesis reaction using dehydration. They're going to actually pull water away from these molecules and attach things together. So it requires energy to do that. So it actually takes energy to build something, which is endothermic. Common type is dehydration synthesis. Water molecules form. So we're going to pull a hydrogen off of one, a hydroxy off the other, H2O. Pull water, form a molecule of water. We're going to attach two things together. And all synthesis reactions in organisms are called anabolism. So if you're not sure of that, like anabolic steroids, they're designed to make things bigger or synthesize things. So just kind of remember anabolic steroids, they make things bigger. It must be a synthesis reaction. Dr. Phil said dehydration synthesis, so we must be forming a molecule of water. Okay? And we're just showing you here. We have to pull a hydrogen off of this and OH off of that, and we combine these two together. And once again, we formed a molecule of water. All right, decomposition reaction. So we're going to break something apart. Hydrolysis, we're going to literally throw water at it. We put water at it, it breaks things apart. Hydrogen goes on one, OH goes on the other. Now we have two separate things. We decomposition. And these literally give off heat, exothermic. All right, and this is called catabolism. All decomposition reactions in an organism are called catabolism. So we have a very large molecule. I'm going to add some water to it. Water is going to cleave or lyse it. All right, so I lose the water. All right, but it gives off energy. Gives off energy, and we break it apart. So we break this bond. OH goes on one, hydrogen goes on the other. Exchange reactions involve breaking and forming covalent bonds. They have endothermic and exothermic steps. So we literally, we can break something and give off energy at the same time. We're going to be bonding things together. So they happen almost simultaneously. And sometimes, as we're bringing things into a cell, halfway through the step, we convert it there and then bring it into the cell as we do exchange reactions in between the cell membrane, and we can change things before they even get inside the cell. We just we know what's going to happen, so we might as well save a step. It's called transport or coport, cisport, things like that. We'll talk about that later. Involve atoms moving from one molecule to another. Some of all chemical reactions in organisms called metabolism. All right. So remember your metabolism, people are, say, what is my basal metabolic rate? That just means, what is um, your basal metabolic rate. So depending on your thyroid function, if your basal metabolic rate is really, really slow, you don't burn a lot of energy, you tend to be cold, a little bit more lethargic. If it's revved up, you tend to burn a lot of energy, you tend to be very active, generally you're thinner. We won't get into hyperthyroidism, hypothyroidism, but metabolism theoretically is all the processes in your body. So that includes the process of breathing, heart rate, muscle tone, thinking, seeing, tasting, all the processes that you aren't even aware of need energy. So just to stay alive, that's your metabolism, where most of your energy goes. A lot of people are thinking, well, you must burn a lot more energy, you're very, very active. Well, that's true, but the vast majority, we could say 1,000, 1,200, or 1,800 calories per day are burned just to keep you alive. That's your basal metabolic rate or metabolism. Everything above and beyond that is energy needed to produce work. All right. So, even if you're sitting at a desk studying or reading or whatever, it's still taking energy. Your brain uses a tremendous amount of glucose just to function. It doesn't, your body will sequester all your glucose if you're low in glucose for brain function. I mean, it'll run on ketones, but it really prefers glucose. And your brain literally uses a lot of energy. All right. So water is the most abundant substance in organisms. Many special characteristics due to two polar covalent bonds. And we saw that specific bond angle of 105 and how the oxygen was slightly negative, the hydrogen was slightly positive. It gives us some very, very unique characteristics. It's cohesive molecules generate surface tension, and you'll see a picture of those water bugs that can walk on water. You'll actually, if it's really calm, you'll see the water just slightly bend, right, from surface tension. It's a little bit more advanced than that. This is actually the fourth property of water, but we won't get into that. It's out of the scope of this course. It's an excellent solvent unless something is lipid-based or wax-based. It isn't a good solvent. Anything that's protein-based, phosphate or your biphospholipid layer of your cell membrane or cell wall. The outer surface is phosphate, which has no problem with water. Proteins don't, but your lipids are in the biphospholipid layer. They're facing the inside. They're hydrophobic. They're afraid of water. All right. Remains liquid across a wide range of temperatures. And once again, your blood or water, you can throw a lot of heat in it. It'll absorb a lot of heat before it actually changes temperature. So it's one of its very, very unique properties too. Oh, here it is. Can absorb significant amounts of heat energy without changing temperature. Participates in many chemical reactions. So, there's hundreds of chemical reactions that are always going to involve some kind of water, whether we're talking about respiration, cellular respiration, or like respiratory system respiration. Uses water. We're talking about making acids, carbonic acid, with pH. So water is just going to be huge in all kinds of reactions. Right. There's talking about the bond angle, hydrogen bonds, and how this very specific structure, the shape, can cause increased surface tension. Right. And the other thing, if you guys want to get some water, get a paper clip and some tweezers, set that paper clip on top of the water flat, it will float. All right. But if you put that paper clip in vertically, it'll sink. But you put it in flat because of the surface tension of the water, it literally will float. Or it should float. But do it carefully. All right. So acids and bases, I'll finish this up and then I will try to process this through WebEx, and it should it'll process the video and then it'll go through and it'll actually convert whatever I am saying legibly, coherently, it'll convert it into closed caption, all right, for you. So acids and bases dissociate by water into component cations. Remember, these are positive charge and anions. Acids dissociate into one or more hydrogen atoms and one or more anions. So acid and base, we'll start talking about pH. Hydrogen, the more hydrogen it has, the more acidic it is, the more base or hydroxyl ions it has, the more basic it is. And we'll talk about the pH scale and how it changes logarithmically with each number of the pH scale. So a base binds with hydrogen when dissolved in water. Some dissociate into cations or OH. That's interesting because you could literally, if you have an acid and you pour water into it, pure water, which is neutral, it will bring the pH up. If you have a base, which is something above 7 in the pH scale, and you dump water into it, it will lower the pH. So literally, water can be a buffer. It can change something from acidic to more basic, or it can change something from basic to more acidic, but it can never completely change it. All right, so your body's gonna have a lot of buffers in them, and they'll actually go in and moderate the pH. And some of the biggest, calcium can do it. Chloride can buffer. It's negatively charged. Sodium biphosphate, baking soda, sodium bicarbonate is very, very basic. It will buffer a lot of acid conditions, especially when food leaves your stomach. It's very acidic. Hydrochloric acid, we'll see coming up, is going to be around 1 or 2. And when that chyme leaves your stomach into the duodenum, it's very, very acidic, and that acidity would kill all of the digestive enzymes from the pancreas. So your pancreas actually excretes some bicarbonate, which is very, very basic, to buffer that acidic content to bring it more towards a neutral 7 and get it, wants to really kind of get it 5, 6, or 7, usually gets it to about a 6, all right? And then the enzymatic enzymes from the pancreas, lipase, or the protein enzymes that will break it down, amylase, will break it down so it is able to be digested. Without bicarbonate, it would be so acidic, it would denature all of those digestive enzymes immediately upon entering the duodenum, before it even got into the jejunum and the part of the intestines. Right. So here's acids and bases. So if it's acidic, when you put it into water, it's going to disassociate into a lot of hydrogen ions, and that's how we get pH. pH stands for percentage, or I guess just consider percentage hydrogen. It's probably the best way to remember it. Right. So if something is acidic, it's going to have a lot of hydrogen atoms in it, and it's actually going to have a lower number. So 0 to right below 7 is theoretically acidic. 7 is completely neutral. So if it's at 7, it has the exact number of hydrogens and hydroxy ions in it. Anything above 7 is basic. It's going to have more hydroxy OH negative charges than it will hydrogen positive charges in it. Here's your pH scale. All right, here is battery acid, sulfuric acid at 0. Hydrochloric acid, remember we saw that chlorine on there, and I said it has those 7 valence electrons. It wants another electron. It goes and takes it from hydrogen all the way to the left. And I said HCl is hydrochloric acid. It's extremely acidic. Your stomach acid is hydrochloric acid, and that has a pH of, I'm going to say 2 to 4, depending on what's going on. But there's lemon, beer, vinegar. Tomatoes are very acidic. Black coffee is acidic. Urine, slightly acidic. Milk, pure water is 7, so that has equal number of hydrogen and hydroxy. Anything above 7 on the pH scale is going to be slightly alkaline or basic. So seawater, baking soda, this is your bicarbonate, sodium bicarbonate. All right, so that if anything acidic, put some baking soda in it. It will raise the pH and make it slightly more basic or alkaline. Milk of magnesia. Have you ever seen that in the drugstore or whatever? People used to drink that for if you had indigestion. Basically, it was pretty much magnesium. You could do the same thing with chewing calcium chalk. Magnesium and calcium are buffers. Household ammonia, don't recommend drinking that. Household bleach, that is a halogen. Chlorine is definitely will kill things by pH scale alone. Oven cleaner, very, very alkaline or basic. So, if you want to spread that on your hands, it'll literally eat through your hands. And the sodium hydroxide is probably the most alkaline basic thing that I can think of. And when I label that at school, it's got a big red crossbones and skull right on it, because a drop or two of that will, number one, eat through your hands. It can also eat right through your clothes. It won't eat through the lab benches. I don't even remember what those lab benches might have, but they were there in 1974 when the school was erected at South Campus. And those same benches were there in 1989 and 90 and 91 when I was doing my prereqs for grad school. Same benches, still there. All right, acids and bases. Metabolism requires relatively constant balance of acids and bases. So in order to have, things, our metabolism, we have to make sure we're in that safe zone between 6 and 8. Now, some processes are going to produce acids, some are going to be very, very basic. So we have to have buffers in place to skew that pH scale into that workable area between 6 and 8. We want something like blood should be like 7.4. We really want to keep it there. So if your interstitial fluid or your blood gets down to like a 6, or it's somewhere up around an 8 or so, that can start denaturing proteins and enzymes, and that can destroys all your enzymes, and then your metabolic activities can't happen, because without enzymes, these reactions would happen, but they'd happen slowly, that it wouldn't be compatible with life. So when people are saying the pH or it's denaturing proteins, it literally is going to denature your enzymes first. And once you start destroying enzymes, you really can't any of the metabolic functions that your body has to do won't happen, because the enzymes lower the activation energy for it and cause these reactions to happen much, much faster. So buffers prevent drastic changes in internal pH. Microorganisms differ in their tolerance of pH. So a lot of microorganisms like the same pH as we do. H. pylori can live in your stomach. It's one of the leading causes of stomach ulcers. But even that is going to start releasing, it has a mechanism that can produce bicarbonate locally around it. So it actually buffers the acidity around it so that the organism can multiply. Many microbes grow best between a pH of 6.5 and 8.5, somewhere in our range. But there's not a lot of places in the body that I'm aware of that have a pH of 8.5. That's pretty basic. In most humans, we tend to run more acidic, which is unfortunate. A lot of our fermentation, a lot of our processes, even carbonic acid from the Krebs cycle, is going to make us slightly more acidic. So if it isn't buffered out by the kidneys or the respiratory system, we generally tend to run more acidic. And one thing that loves acidity is cancer. Cancer loves acidic environments. So unfortunately, that can be problematic. All right, microorganisms can change the pH of their environment by using or producing acids and bases. And H. pylori is one that we're going to learn relatively simply. Some organisms have virulence factors. They can start secreting acids, changing the environment. We're going to find out some of these organisms like Staph aureus can produce coagulase or collagenase, and they can literally start eating through anything that gets in their path. Right. All right, I'm going to end it here. I don't know exactly where I am, but I'm going to end this and process this and put it through. Hopefully it's recording the slideshow and me, so I don't have to do this a third time, because that would really be awful. All right, let me figure out what's going on here. Slideshow. You're sharing your screen. Well, thank you. I'm going to turn the recorder off. Stop sharing. All right, so stop. Oh, an hour. No wonder. Okay.